Hello everyone. Today I will be talking about the behavior and design of fixed-ended steel equal leg angle section columns, which I have worked on as a part of my PhD project at Imperial College London. I am going to first briefly talk about the mechanical behavior of equal leg angles, then I will give an overview of the FE modeling and parametric studies that I conducted. Then I will talk about the current Eurocode 3 design method for angles, and I will finally present our new proposals and highlight the conclusions. First, I would like to address one of the widely discussed topics in the literature for equal leg angles. The torsional and local elastic buckling loads are compared herein. The torsional buckling load is defined by this expression, where the stress in the through thickness direction is assumed to be zero and the Poisson's ratio effect is ignored. If the Poisson's ratio is considered by assuming that anti-clastic plate bending is restrained due to plate continuity, the familiar 1 minus nu squared term appears in the denominator of the warping term. Substituting the definitions of I note, the Saint-Bennett torsion constant, and the warping constant for equal leg angles, we have the following expression for torsional elastic buckling load. Here is the well-known expression for the local elastic buckling load for rectangular plates of width B and thickness T. After substituting the definitions of the plate buckling coefficient and the aspect ratio, this expression can be achieved for local buckling load. Therefore, the torsional and local elastic buckling loads are essentially the same when the restrained anti-clastic bending term is included in the torsional buckling expression. In order to better understand the buckling behavior of equal leg angles, the elastic buckling loads for different modes are plotted against the length. In equal leg angles, since the shear center does not coincide with the centroid, twisting is always accompanied by major axis flexural, although, as it can be seen, for very short angles, torsional buckling is dominant. For short to intermediate angles, the combined torsional-flexural buckling mode is more pronounced. And for longer angles, the critical buckling mode transitions from torsional-flexural to minor axis flexural. Finite element modeling using the commercial software ABAQUS was employed to simulate the behavior of equal leg angles under compression. A four-noded shell element with reduced integration designated S4R in the ABAQUS element library was used. Both hot-rolled and cold-formed angles were modeled. For hot-rolled angles, the root fillet was modeled by introducing thicker elements at the junction between the angle section legs, and the thickness was offset to the outer surface of the cross-section to avoid overlapping of the two legs, which were connected using multi-point constraints. The rounded corner in cold-formed angles was represented by employing a finer mesh in the curved corner region than in the flat regions. The FE models were then validated against a total of 119 existing experiments on steel angle section columns from a wide range of sources in the literature. Here is a summary of the comparisons between the FE model ultimate loads and those obtained experimentally. Overall, there is good agreement between the test and FE ultimate loads for fixed-ended cylindrically pinned and spherically pinned boundary conditions. Following validation of the numerical models, a parametric study was conducted. The FE models were used to generate additional data for both hot-rolled and cold-formed steel equal leg angle section columns, considering a wide range of cross-section geometries and member lengths. The results for the hot-rolled equal leg angle section columns when torsional-flexural buckling is critical are presented in this slide, where the vertical axis is the normalized ultimate strength or the buckling reduction factor, and the horizontal axis is the corresponding normalized member slenderness. In other words, the torsional-flexural member slenderness, noting that the gross area is used in calculation of the both parameters. As it can be seen, for the same slenderness, the buckling reduction factor varies with the torsional flexural to the minor axis flexural elastic buckling load ratio. More precisely, for low elastic buckling load ratios, where torsional or local buckling is dominant, angles show plate-like behavior, and when this ratio increases, angles show column-like behavior. When minor axis flexural buckling is critical, the buckling reduction factors generally follow the column buckling curve. In order to investigate the observed trends in the numerical data, a study into the elastic post-buckling stability of equal leg angle section columns was conducted. The ratio of immediate post-buckling axial stiffness to the initial stiffness is shown. As the elastic buckling load ratio varies between 0 and 1, the post-buckling to initial stiffness ratio can be seen to reduce from 0.44, which corresponds to plate buckling, to 0, which corresponds to neutral post-buckling stability often associated with flexural buckling. The consequences of these changes in post-buckling stability can be seen in the right-hand side figure, where the ratio of the difference between the torsional-flexural and flexural buckling reduction factors over the difference between the torsional and flexural buckling reduction factors is plotted against the elastic buckling load ratio for different stiffnesses. For low elastic buckling load ratios, this ratio is close to unity, signifying that the buckling response of the angle section members is similar to that of plates and approaching the capacity predictions of the plate buckling curve for outstand elements or torsional buckling for equal leg angles. As the elastic buckling load ratio approaches unity, torsional-flexural and minor axis flexural buckling interact, and this ratio reaches a minimum and in some cases falls below the flexural buckling curve when the elastic buckling load ratio is about 1. For higher elastic buckling load ratios, torsional deformations diminish and minor axis flexural buckling becomes dominant. It is concluded from this figure that a new column buckling curve is required to reflect the interactive buckling behavior for elastic buckling load ratios around 1. Next, I would like to briefly touch on the County Record 3 design method for steel angles. In the County Record 3, first the relevant normalized member slenderness is calculated. Then using the parameter phi, which depends on the imperfection factor alpha, the buckling reduction factor is determined, and finally the design member buckling resistance is obtained. Having shown that for equal leg angle section columns, the local and the torsional buckling loads are essentially the same, the current Eurocode is effectively accounting for the same buckling mode twice through the use of torsional-flexural buckling load and the effective area when torsional-flexural buckling is critical. Comparisons of the test and FE ultimate capacities with the resistances predicted by Record 3 are presented in these figures. As it can be seen on the left figure, the current Record 3 is extremely conservative in predicting the strength of steel equal leg angle section columns when torsional-flexural buckling is critical. This is due to the double accounting of the same buckling mode in the local and member buckling checks. Similar comparisons are presented in this table, where there is significant conservatism and high scatter when torsional-flexural buckling is critical. In order to address the shortcomings in the Eurocode 3 design rules, new design rules are proposed. To capture the variation of the torsional-flexural buckling reduction factor with the elastic buckling load ratio, the flexural and torsional buckling curves are used as the lower and upper bounds, respectively, and a new parameter delta F is introduced, which is used to predict the torsional-flexural buckling reduction factor. In addition, a new expression is proposed for the flexural buckling curve to account for torsional-flexural minor axis flexural interaction. In the new design proposals, when torsional-flexural buckling is critical, first the torsional-flexural member slenderness is calculated. The torsional and flexural buckling curves are then used as the upper and lower bounds, respectively. Then the new parameter delta F is used to obtain the torsional-flexural buckling reduction factor, and finally the member buckling resistance is determined, noting that the gross area is used for all classes of cross-sections. When minor axis flexural is critical, the proposed approach is similar to the current Eurocode 3 with the difference of new values for the imperfection factor and introducing a new parameter beta to allow for interactive buckling. The variation of torsional-flexural buckling reduction factor with torsional-flexural member slenderness is shown in this figure for 3 sample values of elastic buckling load ratios together with the F results from the parametric study for columns with similar buckling load ratios. Here are the comparisons of the test and FE ultimate capacities with the resistances predicted by the new proposals. As it can be seen on the left figure, the new design proposals are significantly more accurate and consistent in predicting the strength of steel equal leg angle section columns when torsional-flexural buckling is critical. Similar comparisons are presented in this table, where significant improvements are made in mean values and the reduction in scatter can be seen when torsional-flexural buckling is critical. In conclusion, the current Eurocode 3 approach effectively double counts the same buckling mode when torsional-flexural buckling is critical, and the same reduction factor is predicted for angles with the same slenderness but different elastic buckling load ratios. On the other hand, The new proposals reflect the influence of transition in post-buckling behavior and reflect the effects of interactive buckling when the elastic buckling load ratio is around 1. And in addition, they provide dramatic improvements in accuracy and consistency of strength predictions. I would like to encourage you to have a look at our recent publications where you can find more details on our research and angles. Thank you very much for listening, and I'd be happy to answer any questions.